Euclid's Elements, Book 2, Proposition 5. If a straight line be cut into equal and unequal segments, the rectangle contained by the unequal segments plus the square on the line between the points of section is equal to the square on the half. So we've got a straight line AB. And we're going to bisect it at C and then cut it unequally at D. And what we're going to say is that the rectangle contained by AD DB plus the square on CD is equal to the square on CB. Now the first thing he does is he utilizes proposition 46 to draw our square on CB. Sorry, draw our square on the half. Call this G, call it E. So we've drawn square CE on the half. And then Prop 31, he uses this twice. First, he draws a line from D parallel to CG or BE. We'll call this H. And then also he draws a diagonal BG. But then the other usage of 31 is through the intersection point. He draws a line parallel to BA or GE. And we'll call this F. So we've got two lines. We've got DH parallel to BE, and we've got L, X, and T, and we've got FT parallel to AB. And then from proposition 43 of book 1, we know that the complements about the diameter of a parallelogram are equal, so the complement CX is equal to the complement XE. CX is equal to XE. And then using common notion 2, equals added to equals makes equals, we're going to add the figure dt to both figures in step 4. So we can write that cx plus dt equals xe plus dt. And we can see that the figures cx and dt equal the rectangle CT. And then the figures xe and dt equal the figure DE. But CT is a rectangle formed on the base CB, and AL is also a figure or a rectangle formed on the base AC, but we know AC is equal to CB because we bisected the line AB at C. So according to Euclid's book 36, when parallelograms, in this case rectangles, are on equal bases, namely AC and CB, and in the same parallels, namely AB and FT, then they are equal to each other. So the rectangle AL is equal to the rectangle CT. And then we can utilize, I guess, common notion number 1. We know that AL is equal to CT and DE is equal to CT. Therefore, AL and DE must be equal to each other. So AL equals the figure DE. Now what we're going to do is we're going to add, we're going to utilize common notion number 2 again. Equals added to equals makes equals. we're going to add the complement CX to both of our figures in step 8. So now we get AL plus CX equals DE plus CX. And if we look at these two figures added together, that gives us the rectangle AX. And over here, DE plus CX gives us the gnomon. And I'm just going to call it by the same name as Euclid does. We'll just call it NOP. So it's the complement here, square here, and the complement here. So NOP equals the gnomon NOP. But the rectangle AX is the same. It's made of, essentially it's made of the unequal segments of line AB, because the length AD is equal to the length FX, and DX is equal to DB. So we can rewrite this and say that that is the rectangle AD DB, and then we'll still have it equal to the gnomon NOP. Put step 12 up here. Now what we're going to do both of these in step 11, both of these figures in step 11, we're going to add the square LH to both. Now LH, the square LH, is actually, because LX is the same as CD, LH is technically the same as the square on CD. So we're going to write that. We're going to say that the rectangle AD DB plus the square on CD is equal to the gnomon NOP plus the square LH. Step 13. We're going to leave these the same, so I'll just rewrite these up here. So now we've got AD DB plus the square on CD is equal to the gnomon NOP plus LH, but we can see that gnomon NOP plus LH is equal to the whole figure CE, which is actually the square on CB. So I'll just write it's equal to the figure CE, but the figure CE is the square on CB. Therefore, we have created a rectangle from the unequal segments of B, right here, plus the square on CD, equaling the square on the half, which is exactly what we wanted to do here. QED.